in this example, I want to show that we cannot always simplify differential operators by just multiplying out the so-called factors. So here we'll show that d plus 3t acting on d of y is not the same as d acting on d plus 3t of y. So let's write this out. We have d plus 3t acting on d of y which we can simplify by writing this as d plus 3t acting on y prime and then that simplifies to d acting on y prime and then plus 3t times y prime. And finally, that simplifies to y double prime and then plus 3t times y prime. Now let's see if we reverse the order there. That should not matter for multiplication, but it does matter for the differential operator. So if we take the derivative of d plus 3t acting on y, then what we get is that is the derivative of, and then d of y, that will be y prime, and then plus 3t times y prime, or times y. Now that is important that we have multiplication there, because that means that in order to take the derivative of this, we have to use a product rule here. So the derivative of y prime, that's just y double prime. So that's our first term. But for our second term, we have to multiply 3t times the derivative of y. Or let me actually write this out. I'll write out y double prime plus the derivative of 3t times y. And we have to think that y is a function of t. And so that's a product rule. And so for the second part, we get plus 3t times y prime, and then plus derivative of 3t, that's 3 times y. So this right here needs a product rule. So that gives us this right here. Now, what you see here is that these two outcomes are not the same, because the second part has a 3y that the first part does not have. Now, one can show that as long as we have differential operators of the form a constant times a power of d, then the interaction of the differential operators follows the same rules as the algebra of polynomials. So what went wrong in our previous example is that we included a function of t in our differential operator. So as long as we keep it to powers of d and constants, it follows the same rules as the algebra of polynomials. And that means that when we take a look at systems of differential equations of the following form, and notice the constant coefficients here, a1, a2, a3, a4, a5, a6, a7, a8, then we can use the same rules we used for algebraic systems of equations. So what we can do here is we can simplify the system of differential equations that's written here as a1d plus a2 acting on x, where we think of x as a function of t, plus a3d plus a4 acting on y equals a function f1 of t. And then the second differential equation is a5d plus a6 acting on x plus a7d plus a8 acting on y equals f of 2, or is f2. And we can write that even more compactly if we combine this differential equation, or a differential operator, and call it L1. And then this differential operator, we call that L2. L3 is the operator a5d plus a6, and L4 is a7d plus a8. So we replace this by L1. So we have an operator acting on x, so L1 acting on x plus L2 acting on y, and that equals F1. And then for the second one, we have L3 acts on x and L4 acts on y, and that equals F2. So L1, L2, L3, and L4 are all differential operators, but if we pretend for the moment that they are just constants, like in a normal algebraic equation, then we can use the elimination method to eliminate an unknown variable. And in this case, the variables x and y are actually unknown functions. So if we want to eliminate x of t, then what we can do is we can multiply the first equation, which is L1 of x plus L2 acting on y equals F1. And so multiplying that by L3, second, if we multiply this by L3, it means we let L3 act on that first equation, and then we're going to let L1 act on the second equation. So we get L3 acting on x plus L4 acting on y equals F2. And then we let L1 act on that. And since we can then think of repeated applications of differential operators as just multiplication, as long as they're linear differential operators. We can then subtract these two, and L3 times L1 minus L1 times L3, we can just switch the order there and they will cancel each other out. And so what we're left with is the following. So we have L3 acting on L2. So L3 acting on L2, which acts on Y, and then minus L1 acting on L4, so L1 acting on L4, which acts on Y, and then on the right hand side we have L3 acting on F1. So we have L3 acting on F1, and then minus L1 acting on F2. And this is now a linear differential equation, and it only has one unknown function, namely y. So what you would do then is you would take this linear differential equation and we would solve that for y. And then once you have y, we would then plug in that function into one of the original functions and solve for x. So plug in y and solve for x. Now, I'll leave it up to you to show that you can also eliminate y. Sometimes it might be easier to eliminate y, and we can do that by multiplying the top by L4. So then we get L4, L2y, and then the bottom we would multiply by L2. And if you do that, and I'll leave that up to you to check this, the equivalent differential equation that we get for x would be L4, which is, or times L1 acting on x, and then minus L2 acting on L3 of x, and then that equals L4 acting on F1 minus L2 acting on F2. And then again, we have the same approach. This is a differential equation in x that we would solve for x and then plug in x and solve for y. So we'll do 2 examples in the next 2 videos.